All right, let's talk about a term you hear absolutely everywhere, machine learning. It's the engine behind your Netflix suggestions, and it's also at the heart of some of the most advanced scientific research out there. But what is it really? Let's cut through the noise. We're going to break down how a machine actually learns, and we'll do it by making it visual and easy to grasp. Okay, let's jump right in.
So it really all boils down to this one big question. I mean, we think of learning as, a human thing, an animal thing. So how in the world do you get a chunk of silicon and code to do it? To actually get better at something, to adapt, all on its own? That's the core puzzle we're going to piece together today.
Okay, so if you go and look up the official academic definition, you'll find something like this from Tom Mitchell. It's very precise, very thorough, but it's also a bit of a mouthful, right? Let's boil this down to what it really means in plain English.
That's it. That's the whole game right there. At its heart, machine learning is just about building systems that get better at something by doing it over and over. They learn from that experience instead of a programmer having to write a new rule for every single possibility. And that simple idea, that's the key to everything we're about to talk about.
One of the best ways to understand what something is to first get a handle on what it isn't. And machine learning is a huge departure from the way we've always built software.
Think about a standard computer program. It's all based on explicit instructions. If this happens, then you do that. It just follows a rigid path that a human programmer laid out for it. All the rules are static, they're set in stone. The intelligence is all human. Machine learning completely flips that script. Instead of a person writing the rules, the machine looks at the data and figures out its own rules.
And this gets us to a really key difference in thinking. Traditional programs are deterministic. A calculator is a perfect example. 2 plus 2 is always going to be 4, every time. It's predictable. Machine learning, though, lives in a probabilistic world. It's designed for messy, real-world data, and its answers are more like, I'm 95% sure this is an apple. This ability to deal in probabilities is what makes it so powerful for complex problems that don't have simple if-then answers.
Okay, so if we're throwing out the old rule book, what's left? Well, it's all about patterns. Deep down, you can think of a lot of machine learning as a really sophisticated game of plotting dots on a graph and then drawing lines between them.
And when you think about it, this makes so much sense. Recognizing your friend's face in a crowd, understanding what someone is saying, even predicting which team will win a game, it's all about recognizing patterns based on past experiences. The magic is that computers can find these patterns in massive amounts of data, patterns that you or I would never ever see.
All right, let's make this super concrete. Say we want to teach a machine the difference between an apple and an orange. We're not going to write a single if-then rule. Instead, we're just going to show it a ton of examples. We feed it pictures, each one with a label. This is an apple. This is an orange. This is another apple.
And all those examples we just fed it, that becomes what we call our training data. You can imagine each fruit becoming a single dot on a graph, maybe plotted by its color on one axis and its shape on the other. We're literally giving the machine a textbook of experiences to study from.
So the machine has one job now. It has to look at all those apple dots and all those orange dots and figure out the best possible line it can draw to separate the two groups. And that line, that has a name. It's called the decision boundary.
And that line, the final one the machine settles on after looking at all the data, that is the model. The model is the learned pattern. It's no longer just a bunch of data points, it's a piece of logic, a tool that's now ready to be used.
Okay, so here comes the real test. We introduce a brand new fruit that the machine has never seen before. A new, unlabeled dot appears on the graph. The big question is, based on that line it learned, what is it?
Well, since the dot landed on the apple side of the line, the model predicts it's an apple. Simple as that. And this whole process of using the trained model to make a new prediction, that's called inference. See? We never gave it rules, we gave it examples, and it inferred the rules all by itself.
Now that whole apple and orange thing, that's a perfect example of one specific way a machine can learn. It's called supervised learning. But as you might guess, it's not the only way machines can go about finding these patterns.
First up, supervised learning. We've already seen it. That's learning by example, using all that labeled data. It's perfect for things like spam filters. Then you've got unsupervised learning. I like to call this learning by discovery. You just dump a ton of unlabeled data on the machine, say a huge list of customer purchases, and it finds the hidden clusters and groups all on its own. It might find customer segments you never even knew existed. And the last one, which is super cool, is reinforcement learning. Think of this as learning by trial and error. An AI learns to play a video game, not from examples, but by being rewarded for good moves and punished for bad ones. It literally teaches itself to win.
All right, this next bit is so important if you're ever in a meeting talking about this stuff. It clears up one of the biggest points of confusion out there, the difference between an algorithm and a model. People use them interchangeably, but they're not the same thing at all.
Here's the easiest way to remember it. Think about baking a cake. The algorithm is the recipe. It's the general set of instructions. Mix flour and sugar, add eggs, bake at 350. The model is the actual cake you baked. It's the specific thing you created when you took that recipe and used your specific ingredients, your data. You can use the same recipe to bake a chocolate cake or a vanilla cake. Same algorithm, different model.
So the whole workflow looks like this. Step 1, you pick your recipe, your algorithm. Step 2, you train that algorithm using your specific ingredients, your data. And step 3, the process spits out your final product, a trained model. That model is the thing you actually use to make predictions. The algorithm is the tool you use to create the model.
Okay, for our last concept, let's talk about a challenge that explains exactly why you always hear that machine learning is so data hungry. It's a really fascinating problem, and it has an incredibly dramatic name.
First, let's just get clear on what a dimension is. Don't let the word scare you. In machine learning, a dimension is just a feature or an attribute of your data. For our fruits, the dimensions were color and shape. To describe a person for a bank loan, the dimensions might be age, income, credit score, and location.
Now, here's where it gets kind of wild. There's this rule of thumb, right? For every single new dimension you add to your problem, you need at least 5 training examples. So if you're looking at 10 features, you need 50 examples. That's manageable. But if you have 20 features, now you need at least 100. The data you need just keeps growing.
Exactly. So what on earth happens when you're a company like Netflix and you have hundreds, maybe even thousands of dimensions to describe a person's movie tastes? The amount of data you need to find meaningful patterns becomes absolutely astronomical. And this leads to a very famous problem.
And this is it, the curse of dimensionality. It's this totally wild, counterintuitive idea that just adding more information, more dimensions, can actually make your model worse, not better, unless you add a tidal wave of data to go with it. The data points get spread out too far, the patterns get harder to spot, and the model just gets confused. This is exactly why big data and machine learning go hand in hand.
So let's recap. We've seen that machine learning, at its very core, is about a machine improving with experience by finding patterns in data. We give it examples, it draws a line, and it uses that line to make predictions. But, and this is the big but, how do we make sure it learns the right patterns? What do we do when our data is messy or incomplete, like it always is in the real world? How do we guide it so it doesn't get things horribly wrong? Well, that is where the real art and science of this field truly begins.